Okay, on Tuesday, we talked about this example from Sadai's book. We want to use this example to study how to set up the value of R for frequency regulation performance, and also to ensure the stability. For linear system, there's a necessary and a sufficient condition for stability, which is if we know the transfer function for the dynamic system, we find all the we find the characteristic equation, which is actually the denominator of the transfer function, and we solve all the rules for that characteristic equation. But basically, we just make denominator be 0, and we solve all the rules, which actually are poles of the transfer function. Okay. So each pole means anything you can make the transfer function to become infinite, because if you plug in the pole into the characteristic equation, that will make the denominator be 0. So the transfer function will have a infinite value in the frequency domain. So if all the poles on the left-hand side of the imaginary axis, so this system will be stable. If you're exactly on the imaginary axis, that will be marginally stable, which means there will be a sustained oscillation at the same amplitude. So we want to study the stability for this system with the K, which is the 1 over R, to be determined. So you want to determine a range of K or R such that the system can be stable. And then we can adjust the value to make the load frequency control meet some requirements. That at least we need to generate a normal steady state frequency. Okay, so the first measure we introduced on Tuesday was this Ross-Hurwitz stability criteria. So basically, you just using the formula on the left column to generate a table, which is called the Ross table. In the Ross table, you just use the coefficients of the original characteristic equation to make the first 2 rows. The first 2 rows will basically just come from that characteristic equation. And starting from 3rd row, you're going to utilize those formula to come up with each element. So until all the new element will be 0, so it just stop. Okay. So what you need to do is just make sure the first column to be all positive. Then the system will be stable. So for this specific problem, we know if we make a first column to be positive, any item having K has to be positive. Then finally, we can easily conclude the K has to be smaller than 73.965. Okay, because R is 1 over K, which means R has to be bigger than this value. So 0.0135 is the minimal R you can use. So if you take R exactly at this value, the system will be marginally stable. Marginally stable means it has oscillation, but the oscillation is not growing. It will just stay at equal amplitude, but which is also not good. This lecture, we're going to talk about the second method, which is called root locus method. This root locus method is the most straightforward to give you an idea on why the system become unstable when you're changing K. The Ross table method is good for you to work on, like use some algebra to figure out the inequality constraints, so some equation you can solve and no variable. But this root locus method is give you more visualization to tell why changing K will cause instability. So this is the open loop transfer function. Okay, so I color the 3 factor. Each will give you maybe 1 root of this this to make the denominator be 0. Okay, so those 3 roots will tell you the 3 poles of the open loop transfer function, not closed loop transfer function. But when you try to write down the closed loop transfer function, so it's defined to be the the forward component from the input to the output, which is the GS, divided by 1 plus the open loop transfer function. Okay. Then you do some simplification, you will have this one. So this is a closed loop transfer function. So this one will tell you the stability. You have to make sure all the roots are in the denominator to be on the left-hand side of the imaginary axis. Okay. So then you know, so actually when k change the value, like for instance, if k equals 0, the open loop transfer function's pose will be closed loop transfer function pose. So if k equals 0, so what are the poles of the closed loop transfer function? Will be the one, there's a, like this one will have, one pole will be s equals 0.08, right? And this one will be s equals, oh, this is negative, right? Negative 5. And this one will be negative 2. So there are 3 poles with the open loop transfer function. So if k equals 0, so which means the open loop transfer function can be the closed loop transfer function's pose. Then when you increase the k, and the poles of the closed loop transfer function will move apart from the open loop transfer function. So when k increase to infinite, so those open loop transfer function will not be important anymore. Okay, so if the system has any, if the open loop transfer function has any zeros, which is show up here. But for this case, there's no 0. But if you assume if this is some 0, we put it as plus z. So that as that 0 will appear here, right? And when s increase to infinite, so that will make those open loop transfer function pole not important anymore. But open loop transfer function 0 will become poles. So they tell, so if I increase k from 0 to infinite, the open loop transfer functions, the poles will determine some starting point of the closed loop transfer function poles, and 0 will determine the final points of the closed loop transfer function. So that's why we can draw the locus of each root, how it moves with k increase. Then by stopping the k value at a certain boundary, which is the imaginary axis, will know the stability limit. So that's the idea. So you can, if you use MATLAB, you can just you can call, there's one function which can draw this root locus, each root locus for you. So you see, I color them differently with red, green, and blue. So that indicate, for instance, this red root locus will starting from this one. So that pole will be coming from the red factor. And there's a green one will be coming from here, and the blue will from there. Okay, so we will increase k, so the root, the closed loop transfer functions roots will, or poles will move away from those x. And for this red locus and the green locus, they will finally intersect with the imaginary axis. The system will become unstable. So we just need to stop there. We need to figure out the k value at those 2 critical points. And that will be the limit of k. Okay, so if you know how to use MATLAB, you can just tell MATLAB this transfer function, it will draw this root locus for you. So that value exactly tell you the k is equal to 73.965. It's same as the result from the Ross table method. All right, so if you read, there's appendix with Sadek's book, it gives you more details, description about the step or the method of this root locus method, but those are good for people without computer. So in the past, if you have no computer, you only have this equation, you need to do by hand to draw those root locus. Definitely it's not accurate, but they will give you pretty good estimation. But we don't need to do that anymore. But if you like, you can try those steps. But this basically explains for the open loop transfer function, you have a number of poles and you have a number of zeros. And when you generate this closed loop transfer function, so those poles will be here, right? Those zero will be multiplied by k and put on this item. So when k increase from 0 to infinite, first this one will play a dominant role to determine where the poles are. And later when k is large enough, 0 will play a dominant role. So that explains why each root local will start from the pole and going to infinite. But because for this case, there's no 0. The only 0 is infinite. So all root loci will finally go to infinite. There's like more detail to tell you how to draw each individual root locus. For instance, okay, like for instance, the third element, the root loci on the real axis always lie in the section of a real axis to the left of an odd number of poles and 0. So what does that mean? So when you solve using the open loop transfer function to find out those 3 poles, in order to determine which section belong to a root locus, so that tells you this section has to be, because on the right-hand side, there's a 3 poles, which is odd number. And this one cannot be root locus. And the one in the middle of the next 2 has to be, because on the right-hand side of that locus, there's only just 1. And this one cannot be, because on the right-hand side, there's a 0. So that basically, so the first step is just you identify those poles on the plane or on the axis, and then you try to decide which section belongs part of the root locus. Okay, but there are some other root loci will go to the infinite by certain angle, not stay on the real axis. So that angle can be solved by here. Okay, for this case, that angle is 60 degrees. But if you have a more complex situation, you will see the root loci will have more weird shape, but that can be estimated here. Definitely, we don't need to do that anymore. But this one gave you a better realization on why the system can lose stability. Okay, I suppose everyone already learned some of this knowledge, right? If you already taken linear system, this should be a necessary knowledge you have to know. Yeah, but if you want to do homework using the root locus method, you can definitely call that MATLAB function. So you go to find this example from Sadek's book, and then you can find the code. So that code will give you that file name. I already upload that toolbox. So you see here, you just try to identify this file name. I'll give you that example and also all the functions you can call to calculate the ROS table or the root locus for you. Any question? All right, so after we know the limit, which is 0.0135 for R, we have to select R bigger than this value. For instance, if you select 0.05 per unit, based on the calculation, we'll have a 0.576 Hertz frequency deviation, which is actually higher than the half Hertz limit we usually use. If you don't use any load frequency control, only using the frequency sensitive load to somehow mitigate the frequency deviation, so the frequency can be very bad. So it will end up at like 45 Hertz because the deviation can be 15 Hertz without load frequency control. This corresponds to the case with R equals infinite or K equals 0. Basically, you just open the feedback link in that block diagram. If we make R be 10 times bigger than the limit, the frequency deviation will be around 1.4 Hertz, which is also very bad. If you make R be exactly at the limit, then you will see the frequency will be oscillating forever, right, at equal amplitude. Even you check what is the steady state deviation, you just need to find the central value of this waveform. That central value is not zero. Zero is here, so it still has certain gap to zero. So this central value is around the negative 0.2. So you still have about 0.2 hertz deviation. Even you take this maximal gain at the stability limit. So which means the low frequency control may not do perfect job to mitigate the frequency deviation. You need another type of control, which is AGC. So when you design the proportional controller, try to control some variable based on some preset value. Only using proportional control, it cannot give you accurate the final value, and it can also encounter some stability problem. So you have to use other type of controller like a integral controller, or you can also add differential controller to give you better performance stability. Okay, so next we want to talk about the realistic turbine governor system and also its model, because you may not use the model we talked about so far in your stability study. You may be able, very likely you will use more complex model, right? But now you understand for the simplified governor turbine, if we treat each component as a linear system, we already know how to design R. This slide is still valuable. If you know the total time constant for each component for governor turbine, and you know the swing equation, including inertia and the frequency sensitive load, you'll be able to design R or determine the range of R. But if you want to do simulation, time domain simulation of this generator, subjected to some large disturbance, small disturbance, we need a better model. Okay, so what is a more accurate turbine or governor model like in stability study? So this just show the turbine governor system. Basically, just use the coal-fired power plant as one example. The coal-fired power plant is working based on the principle to generate a lot of high pressure, high temperature steam in the boiler. For this case, the fuel will be the coal, but definitely you can use this similar idea for nuclear power plant. The nuclear power plant, the nuclear, the fuel will not be a coal for that case. But anyway, so the boiler will generate high pressure, high temperature steam, and go through this high pressure turbine. It will drive this turbine. The shaft will speed up to generate the speed for the rotor. And when the high pressure steam is leaving from this high pressure turbine, we want to reuse the energy carried by the steam. So we will go through this reheater and come back to the medium pressure turbine. So we can utilize that energy, and we can add another link, which is like low pressure turbine. So finally, if we cannot utilize any mechanical energy from the steam, so it will go to the condenser, right? It will go to the cooling tower, become ambient temperature, then it will come back to the boiler. So we'll go through this cycle. So which means if we model the turbine system more accurately, definitely we need to know the total time constant, right? The total time constant means for this entire cycle, how much time it will take, right, to translate the information from like the valve opening on the valve opening on the pipe to the mechanical power chain. So this time may take maybe less than 1 second or maybe some time, but only knowing the total time is not enough. It doesn't give you the accurate modeling. So we have to model each component. So this is the type 1 speed governor model defined by EECS. Okay, this is very widely used model. So if you compare that model here, so we can translate, we can explain what each component means. So you see on the the top left corner, that's speed deviation. Speed deviation goes through this first component, which is what is the dead band, yeah, which is dead band. So by that dead band, you can define how's the sensitivity of the governor. So for instance, you can define like 0.03 hertz or 30 millihertz. Okay, so only when the deviation is bigger than 0.03 hertz, that speed deviation signal will go through the bottom one. The bottom one just means there's some K, right? K just means 1 over R. That K is exactly 1 over R. For this specific model, that K is equal to 20. So R is 0.05. All right, so next they will go through this component. This component will have some time constant. That time constant together with this time constant, total T1 plus T3 will be roughly the time constant for governor. The tau G we used in the early slide. And everything starting from here will belong to the turbine. We'll translate the valve opening until the mechanical power change. So you see there's two group of models, right? The top one will be high pressure turbine, and the bottom one will be low pressure turbine. It will be modeled the high pressure and the low pressure. Definitely, if you want to model the medium pressure, you can do that, but usually this can be good enough. So it's modeled time constant of each component, each step. So the linear model with the total time constant, actually that tau T is roughly equal to the summation of the sum of all the time constant here. But this one gives you better details. So you may raise the question, so what if I don't need this detailed model? Is this model structure useful to me? Yes, you can just go ahead to plug in the value from that linear model here, right? For instance, I only know the total time constant for the turbine. You just make this T4 to be that value. Anything else will be 0. Just make it be 0. Okay, if you ignore low pressure turbine, just make those K to be 0. So you still can borrow this structure. And for each dead band or for each limit, if you don't know the limit, you can make it be large enough. So this model structure is still very useful for you. So you can generate the model parameters based on what you already know. For the parameter you don't know, you either just set that one to be 0, such as for dead band, or you just set up like very large limit. Any question? So in the final project for the course, we're going to utilize this model, okay, in the study. Next, we want to come back to this closed loop transfer function, and we can explain so what determines the final steady state frequency of the system. So with both load frequency control and the frequency sensitive load, utilizing this closed loop transfer function. So under steady state condition, we just make S be 0. Then the frequency deviation. So if I use omega, so usually I assume that to be per unit. Okay, this is just to be consistent with the Sadek's book. And if anywhere I use delta F, usually I assume that one to be hertz, which is actual frequency. But if you specifically mean delta F means per unit, that's actually exactly same as delta omega. Okay, delta omega SS will be steady state frequency, which means originally the rotor speed to plug in the S with 0 value. So basically that just take off, make every basically make every item multiplying S be 0. So finally, this is the steady state frequency. We already derived this formula. Another thing we can study is under steady state condition, how does the frequency influence the change on the mechanical power? So this this will be the static frequency, right? They will first go through this 1 over R, then come back and go through this component and that component, governor and turbine, because both governor and turbine under steady state condition at 1. So this one become 1, that become 1. So basically it's just a steady state frequency multiplied by 1 over R become delta PM. So delta PM is really proportional to the speed deviation with the coefficient which is negative 1 over R. That negative came from the negative feedback, the negative sign. So now we have two equations talking about the steady state frequency deviation. So those two equations have to agree with each other, right? So from this one, we know the steady state frequency will be negative delta PM multiplied by R. Okay, next, we just bring the two equations together. The first part will be exactly the same as this equation. That one tells if frequency under steady state condition changed by this value, that will be reflected on the mechanical power change on each generator. How much is changed depends on the R. If I have a bigger R, its delta P will be smaller. If I have smaller R, delta P will be bigger. So this is steady state frequency. It means really the final system frequency of the entire system after all the transient dynamic have been finished. Okay, but second equation tell this frequency deviation depends on the load change on the system. It's equal to the negative load change divided by this factor, which depend on the D, which is the overall the frequency dependency of the load. And this is like a total regulation of all the generator. Okay, so that's interesting. So that will create this equation. The left on the left-hand side only depend on each unit. The right-hand side depend on all the units. So what does this one mean? So if you visualize this relation, which means if I have a load change on the system, the load change from this equation, from the second one, the load change can be translated to the blue atom and the red atom. The blue atom is equal to the speed deviation divided by R. Okay, and this means the change, the mechanical power change due to the generator. And the second item is the change due to the frequency sensitive load. So if my system right now is operating at 60 Hertz, okay, and I increase the load by maybe 10 megawatt. Finally, when the system becomes stable again, right, at a new steady state frequency. So if that new steady state frequency is not 60 Hertz, it's like 59.9, there's negative 0.1 Hertz deviation. Okay, that 0.9 Hertz drop will change the load, will make my existing load not be the original like number minus 10 megawatt. The actual load will decrease because they have sensitivity to frequency. My governor also need to change, okay, to pick up to balance the load. That's what this one means. So if I visualize using those two figures from a Quinter's book, so I have a generator to power. There could be two type of load. Okay, the first type of load is depending on the frequency. It's linearly depending on the frequency deviation, and the second part doesn't depend on frequency. So if I assume there's a change on this load, that change will be coming from both change of the generator and the change on the frequency dependent load. So what this equation tells is the total change on the load on the frequency insensitive part is equal to the change on the mechanical power minus change on the frequency sensitive part. Another interpretation is whatever output from the generator will go to two branches. Okay, one path will go to the frequency sensitive part. One path will go to the some power will go to the frequency insensitive load. That's what it means. And I can also use this triangle to explain what happened. So S is actually the power change. The power change can be about load change, mechanical power change, and Y will be the frequency deviation. So if a frequency drop, the delta F will be going down, will become negative. Then I can draw this triangle. So on this long edge, that is delta PL. That's a total load change. That total load change will become two parts. First part will be reflected on the generation change. But the generation change is not equal to the total load change because I do have a frequency sensitive part. Because that frequency sensitive part, I don't need to change that much. I only need to change less than the load change. Okay. Then there's another two edges. So this one will have slope, which is negative R. And this one will have slope, which is positive 1 over D. So those two equations will come up here, become that equation. All right. So this one is plain. When you have a load change, the load change is estimated based on the original frequency. But once that load change is added to the system, the frequency will change. Because the frequency change, the remaining load will not be exactly the same as the original load because they're operating at a different frequency. So what the remaining load appear will be slightly different. And also your generation need to be changed due to the governor. So in order to have the power balance, finally, the change will be reflected on both of the generation and also the frequency sensitive load. And they together determine the frequency deviation. So if we color those two triangles in blue and red, which indicate how each component can influence the final frequency deviation. So let's consider extreme condition. So what if I have no load frequency control? When I have no load frequency control, so R will be infinite, right? So when R equals infinite, which means this line will become a vertical. So which means I push the boundary between the blue and the red to the left to make this red triangle to be this one, right? It's still similar with the same slope. But now the frequency deviation becomes really huge without load frequency control. Another scenario is what if all my load is a frequency insensitive, so which means D equals 0. If D equals 0, this load will become infinite. So this line will be vertical, and I push the boundary between the blue and the red to the right boundary. So what happened is I have this new blue triangle, and the frequency deviation will be bigger. It's not as bad as that one, but it has increased the frequency deviation. Any question? Okay, next we are ready to try some examples with multiple generating units, not just single one. So there could be a number of things we need to deal with. First of all, each generating unit has its individual R value, and the R value is calculated based on how the power change, how the power change to respond to the frequency deviation. Okay, if the power change is estimated based on the per unit value, we need to be careful to check which base is used for each unit, because the two units may have different ratings, so we have different base values. So we may have to define a common base to recalculate those per unit value. Like for example, in this case, we have two units. The unit 1 has 600 MVA as a rating, which is also the base value of power. The speed regulation factor R is 0.6. Unit 2 is 500 MVA and R is 4%. So there are two cases. Assume the unit 1 is supplying the 500 megawatt power and unit 2 supplies 400. Both operate at 60 hertz and the load is increased by 90 megawatt. So we need to figure out the change on the frequency and also change on the mechanical power of each unit for two cases. The first case, assume there's no frequency dependent load, which means D is equal to 0. The second is the D is equal to 1.5 because load will change by 1.5% for every 1% change in frequency. So for both cases, we need to solve the new outputs of the generators and also the new frequency. Please note the two units have two different ratings at their MVA base. Okay, so when we connect the two units together into the same power system, we have to select a common power base. For instance, like we can select 1000 MVA. It will be fine if you select any other common base. For example, you can select 600 MVA as a common base. Then you may need to update the calculation for the second unit. But for this case, if we select a common base different from their original base, we need to update the per unit value for both units. So let's see the P is actually in the unit of megawatt or MVA, okay? So which is equal to the per unit value multiplied by the base. So if there are two potential bases, so this equation has to be true, okay? So this is the actual value is equal to the per unit value multiplied by that base. So which means if we already know the per unit value of base 2, and also we know the base 2 and base 1, we will be able to translate from a per unit value on base 2 to the per unit value on base 1 using this formula. Then we come to this equation. The static frequency deviation is equal to the negative delta PM, which is the power change on each unit multiplied by the regulation factor, and also depend on the load change. Okay, so then if the power right now is taking a base value, taking per unit value on the base 2, the frequency deviation will be equal, just that formula, I just make the P here to be per unit value multiplied by the RB2. RB2 will be the value calculated based on the base 2. And this one should also be true if I switch the base. The change of the base doesn't change this equation, okay? Then by utilizing the second formula on right to translate per unit power from base 2 to base 1, I can just plug in the delta P base 1 by here. So it will get that formula. Then immediately we can get this equation because we can compare this part to that part. They have to be equal. So immediately we can have, so those two have to be same. Right, so yeah, so immediately we have this equation. Okay, so if I have a R value, like for example 6%, calculated based on the base 600 MVA, and now I want to translate this one to another base, either this one or 1000 MVA. So I need to select the new base here, then I get a new R value. So the regulation factor can change if I change the base. Let's try this common 1000 MVA new base. So R1 right now becomes 0.1 per unit. R2 become 0.08 per unit. So they're both increased because we're using a much bigger base. So the power change in the common base will be 90 divided by 1000 will be 0.09 per unit. So next we can do the calculation for the two cases. First, if we have no frequency dependent load, which means that red triangle doesn't exist. Okay, so entirely the frequency deviation is caused by that blue triangle. So in this formula, we don't see the D. D is not shown in the denominator. So the frequency deviation is negative 0.004 per unit. Okay, translated to the hertz will be a negative 0.24 hertz. New frequency will be 59.76 hertz. Mechanical power change will be 40 megawatt for unit 1, 50 megawatt for unit 2. 40 plus 50 will be exactly 90 megawatt. So this one determine if I have to change load by 90 megawatt, and the change will be distributed among the two units. And the first unit will take over 40 megawatt change, and second will take a 50 megawatt change. The change due to the frequency is 0 because there's no frequency dependent load. For the second case, if D equals 1.5, that is based on the system before disturbance. And after the system has disturbance, the total load will change. But here we just assume the D will stay about the same because the load change is only a very small compared to the total load. So now to calculate the steady state frequency, we have to have a D in the denominator. So that will give a slightly smaller frequency deviation. Okay, translated to the value in hertz, that will be the final frequency will be 59.775, right? Slightly higher than the first case. So which means when your system has a frequency sensitive load, any load increase won't cause as much the frequency deviation. The power change on each unit will be 37.5 megawatt on unit 1 and 46.9 on megawatt on unit 2. The load change due to the frequency deviation will be negative 5.6 megawatt. Okay, so now if you add those numbers, just ignore the negative sign of the last one, but add the number, they give you exactly 90. So if you, so now after this load change, the units 1 and 2 will supply, the first unit will output 537.5, second will be 446.9, okay? And the frequency will be 59.775. And the total power generation change, if you add those two numbers together, that's 84.4 megawatt, okay, different from 90. So we have change on the load, which is 90 megawatt, but actually the load is the generation only changed by 84.4 megawatt. It doesn't need to increase by 90. Why? Because frequency is not 60 hertz. If this is 60 hertz, this one will be 90. If this is not 60 hertz, if it's lower than 60, the 90 megawatt change here on the new frequency become smaller because frequency drop. And that is confirmed by this value, okay? Because there's a frequency dependency will cause a change, which is negative 5.6, which means your load increase doesn't need to be 90. It will only be 90 minus 5.6, which is 84.4 megawatt in the new frequency, which is lower than 60. Okay, any question? Let's visualize how the generation and load change in this figure. The X will be the per unit output of each unit, and Y will be per unit frequency. So there are two straight lines indicating the the low frequency control characteristic of each unit, because the slope is negative, all right, because it's droop control. So when the system operates at 60 Hertz, those two lines will intersect with this red line at 2 points. Those 2 points will be the original generation, right? Because here the base value is 1,000, so 0.44 times 1,000 will be 400. So there's a 400 megawatt and 500 megawatt, right? And those could be the 2 points reflecting the generation dispatch. So if you have an electricity market, you have economic dispatch, the dispatch will determine their output, like 400 or 500 at 60 Hertz. And to give you the minimal fuel cost or maybe the largest benefit by solving optimization problem. So now the load increased by 90 megawatt. And based on our calculation, the frequency will drop to 0.996, okay? So by decreasing this frequency, and you see the both intersection point will move to the right. So that will increase the output from 400, 500 to what's the value, like 450 or 540. So just make a total increase to be 90. So now the new operating point will be those 2 points. That's the case without frequency dependent load. If there's a frequency dependent load, the frequency division will be smaller. So the 2 units will still increase their outputs, but they don't increase as much as the D equals 0 case. Okay, so what I want to say by this figure is, so when you operate system at 60 Hertz, you can solve some generation dispatch or economic dispatch problem to find out the optimal outputs of all units, right, for the minimal fuel cost. That's the result from an economic dispatch. But once your frequency change, their output will also change depending on their R value. If they have different R value, they can change by different, based on the droop control. So their new output may not be same as the optimal dispatch result. So if we ignore the frequency sensitive load, the frequency division will tell how much you change on the unit 1 and how much change on unit 2. If you add the change to the original value, the new value may not be the optimal one. So you either need to resolve the dispatch problem to find out the new output, or you can adjust those R value to make sure their output the new output will still be optimized. Because if you don't set up those R1, R2 properly, their change will be deviate from the optimized value. Okay, so you may need to consider the economic dispatch by selecting the R value, unless you don't care. But definitely, if you have a AGC, you can always bring the frequency back to 60 Hertz, then don't worry. So this one will temporarily increase maybe your fuel cost during the transition of the load change. Any question? All right. Okay, so next we can talk more about the frequency response characteristic for the entire system, not just a single power plant. If you have a many power plant, like N power plant together to support the load of the system, and if we study how the frequency change, and if we don't need very accurate simulation, we can just calculate the total inertia. The total inertia will reflect how quickly the frequency can change with any load or generation change. So then we need to discuss on the the low frequency control for multi-generator system. So here, we can assume all the generator are coherent. At least if we study one area, each area will be coherent, such as we can use equivalent generator to represent the entire area. So here M is actually the how much time you take from maybe the zero speed to the regular to the nominal speed at the rated power, right? That's basically M equals double H. If you calculate the total H and multiply by 2, that will give you this this M equivalent. We also need to calculate the equivalent R for the entire system. So using this parallel circuit rule, we can just calculate the R equivalent. Then the frequency division will be determined by still by this equation. This one we already proved. Then we have to use a new concept, which is called frequency response characteristic, which is an index reflecting how one area respond to the load change or the generation change or the frequency. So this frequency response characteristic is also called the frequency Bell's factor. Usually it's use beta. So beta is simply just defined to be the total D plus 1 over equivalent R. So the unit usually is megawatt per 0.1 hertz. So it's not megawatt per hertz because 1 hertz deviation is huge, right? 0.1 hertz is already very large for most of the normal condition. So this factor tell you for a system how much megawatt power can cause 0.1 hertz change. So if a beta factor equals 1, which means 1 megawatt will give you 0.1 hertz frequency division. Okay, that's very sensitive system. So usually the beta value need to be large, right? The bigger beta, the better for the system. And there's a frequency disturbance. So this beta value of the FRC depend on the governor group settings based on the R value. It depend on the equivalent R. So if any generator change the R, because here all the R's are considered as like a parallel branches of circuit. So any R decrease, okay, that will significantly influence the final R. The final R equivalent depend on the most sensitive governor. Okay, if you make one governor to be very sensitive, that will change the R value, which means that governor will take over the frequency control for the entire system. Okay, so I just show this as my last slide. So this one gives you idea on the beta value for each interconnection. For the Western connection, the beta value is 1,600 megawatt per 0.1 hertz. So in order to see 0.1 hertz frequency change, you are going to change the power in either generation load by 1.6 gigawatt. So that's huge, right? For the Eastern connection, that value is a 4 gigawatt. In order to see 0.1 hertz frequency deviation, the load of generation had to be changed by 4 gigawatt. So you can imagine in most of the normal conditions, the frequency deviation is very small, much less than 1 hertz, which means the Eastern connection has much better frequency, closer to the 60 hertz value. And the ERCOT system is smaller. So to have 0.1 hertz frequency deviation, only 700 megawatt can make it happen. The 700 megawatt already close to maybe the total power of like a wind farm. Like Texas has a lot of wind farm. What if those wind farms just stop? So that already can give you large frequency disturbance. Okay. All right, so this is my last slide for today. Next week will be a spring break, so we'll come back 1 week later.